Yeah. In the last class, we discussed about how to handle data analytics using Unix tool, that is AWS. So we discussed, so understood what is weather dataset, how weather dataset is being captured, and of course, uh, apart from this, what is the structure of a weather dataset? We discussed all these things, and we discussed how your Linux program, you can certainly write this AWK program. So certainly you add 0 to the reading data, so automatically it becomes a number. Okay, and the same thing you compare with the maximum, and finally check for the final data, final maximum value display. This is what we discussed in the last class. And in today's class, this is what discussed. So almost it took 42 minutes. So in today's class, we have a component. We have a component to discuss about MapReduce. To discuss more about MapReduce, we have the component right, and you observe here MapReduce. Why MapReduce is required? So one very important concept that you understood is, so it is straightforward that other tools can also process data, but MapReduce, when we use, what happens? We can certainly achieve parallel processing. You see, many maps are working on the same big data. Many maps are working, and of course, they do a lot of other stages. They certainly work, and finally they reduce, and you get the output, final output. So, in theory, this is a straightforward that we could process a different years data in different processing. So that is different processes will process different years. So we understood that in the data set what we have chosen, we have data from 100 years data. So at least 10 years data, 1901 to 1910, if data is given to one process, 1911 to 1920 given to another processor, 1921 to 30 another, like this. Every 10 years data, if it is given to each mapper, so mapper is nothing but a separate process. So what happens, it creates a separate process thread, and that process thread certainly will handle the entire processing. So that is what I was just talking about, and of course, so using different data, using all the available hardware threads, we can certainly have this data processing. This data processing can be done, and of course, whenever we have such ideas, definitely we encounter some problems. However, what are these problems? First problem is, so how to split the data into an equal chunks? Who will do this? This is one very important thing that we should understand. So 100 years data we are having, and we have identified some 10 processes. And who will exactly do the splitting of this data? So data set splitting, who has to do? So splitting of data, who has to do? That is the first problem that we have understood. Second is combining the results from independent process. So if the process certainly executes and finally they get the results, and who will get the final results, final output, who will going to get? So that is the thing. So when we start using multiple machines, of course, these mappers and these reducers, whatever we are using, they are not used in the same machines. Of course, they are executed in various other machines. So when they are executed in various other machines, what happens? They can certainly have the concept of some coordination. So when multiple tasking is happening, multiple processing is happening, somebody should coordinate. Coordinate in the sense somebody should you know take initiative or to control something, and they had to do. When we start using multiple machines, a whole host of others come into play. That is mainly falling into the category of coordination and reliability, and that should be a reliable one. That should be a reliable one. And who runs the overall job? How do we deal with the failed process? So this is what we have to understand. So if some process is failed, how to detect? What is the alternative thing? Who will going to monitor all these things? Who will going to actually process all these things? So these are some of the issues that has to be understood and addressed. It should be understood and addressed, and that is what uh, uh, the basic preliminary task before we should actually process this data. So, of course, the big data, we have mappers, we have reducers. Finally, we understood that the result will be combined into one, and all those things we understood. So, finally, though it's feasible to parallelize the entire processing in practice, don't you think it is a messy? So you see, after map operations, what happens? There will be a reduce operation. So 2-3 maps will reduce into one result. And the reducer will take care, and it will be reducing further. So that is what we certainly have. So using the framework like Hadoop, Hadoop has a concept of just like a name node and a data node. We have name node and data node, for storing the data. Similarly, we have job tracker and task tracker. These are the two components that are there. For handling, to take care of this entire parallel processing, to make a coordination of all these processing. Of course, you can certainly understand that using a framework like Hadoop, Hadoop has a framework. Inside the framework, we have task tracker and job tracker. The job tracker will track the entire complete job, and entire complete job is split into small jobs, and all these jobs are tracked. And of course, in case of any failure, in case of any problem, so it will automatically be reduced and sorted out and analyzed. Of course, Hadoop. So unlike any other parallel processing framework, Hadoop framework take care of all these above issues what we have discussed. So who will going to split? Who will going to reduce the results? Who will going to monitor the entire processing? And who will going to consider the failure? All those coordinate the failure, and all those things will be easily managed by Hadoop systems, Hadoop ecosystem. So that is what we are supposed to understand. And of course, you see, in Hadoop, actually, we know very well there are two critical components. One is storage component. Storage component is your HDFS, Hadoop Distributed File System, where it will store the data efficiently across all the data nodes. So, it will certainly do it. And second one, HDFS. Second one we have is MapReduce. MapReduce is a processing system. How exactly MapReduce will support this distributed parallel processing. That is what we have to understand. So you have seen how MapReduce works for a small inputs. In the beginning of this particular module, I have just explained how exactly MapReduce works with small data sets. I have taken a small data and that is to count number of number of frequency of each word in a text file. So we have understood that. We have analyzed. Okay. So now it is the time to take big view, big data. So to view the system and look at the data flow for large inputs. So once you give the data, your data is split into small parts. It will be split into small parts, and later it will be sent for exact processing, further processing. And once it is further processed, so what happens? It will be converted into one simple output, which you call it as a reduce phase, map phase, and finally the results, whatever you are getting out of this entire processing, will be sent back. So you know very well HDFS, there is a command called copy from local. The big data will be copied from your local system to your Hadoop system. Processes here, entire thing is processes here. Finally, once you get the output, whatever the output that you are getting, that will be again, it is in the Hadoop system itself, HDFS. So it will be moved back to the local system. Local system means the operating system, local operating system. That is, so move to the local system. So copy to the local system. So it works just like that. And of course, for simplicity, the examples so far have used files on local files. And of course, for all these things, we have understood the entire operation should happen in a local file system. And finally, the result should come in local system. But the processing, the entire processing, whatever we are having, the entire processing is happening inside your Hadoop environment. Data is taken from local system and split, stored in HDFS, processed, and finally the results are sent back to the local system. So that is what we have to understand. However, to scale out, we need to store the data in a distributed file system, typically HDFS, to allow Hadoop to move the MapReduce computation to each machine, hosting a part of data. See, the big data is split into small portions, and these small portions are what we call it as blocks. These blocks are sent to each computer, each data nodes. And in the data node itself, what happens? The processing happens. And the splitting work, we call it as a map, and joining work, we call it as reduce, of course. So finally, we get the result. So it is just like that. And of course, for this, in order to have this coordination among the entire processing and coordination among splitting the entire task, entire job into tasks. So again, it is a very challenging thing. So MapReduce will work only when there is a ready data. And of course, every computer has a MapReduce functions running, right? So when it is running, somebody should identify the process and track this process, understand this process and track this process. So you have job tracker. This usually job tracker will be running in the name node. Name node is the actual master node. So in the master node, actually what happens, the job tracker is running, and job tracker takes the job from the client. You see, is taking the job from the client. This job is, split into smaller jobs. The smaller jobs you call it as tasks, and these tasks are given to each computer. And of course, you see, it is maintaining a thread. It is having a thread. It is maintaining a thread. It is having a thread. Through thread, it is going to handle. That's why Hadoop is written in Java. We have understood in the beginning itself. So Java supports multi-threading, and using that threading concept only, what happens, this entire parallel processing is tracked and coordinated. That's very important thing that you should understand. So the jobs are split into tasks, and each task is given to each thread, process threads, and using that threads you can manage. And each task has again two components. One is map component. Observe here, map in the picture, map component and reduce. Again, map works first. The result of the map is sent to reducer, and all these reducers again will send the result to another reducer, and again another reducer will return back the result to the job tracker, and job tracker will again give the result to the client. Gives the result to the client. So this is what things that are going to happen. So look at the first point. The map reduce job is a unit of work. It's a unit. It's a piece of work that the client wants to perform, wants to be performed. It consists of input data, the map reduce program, and configuration information. So it has all these things. Now, Hadoop runs the job by dividing it into tasks. So this is the entire job that is being submitted by the client. The job, whatever client has given, that is subdivided into tasks, of which again the tasks are internally being executed in two tasks, that is map task and reduce task. So there are two types of again nodes to control these job execution. One is job tracker and task tracker. Now job tracker works in name node. The task tracker works on the system where the actual data is present. That means it is in data nodes. So data node is where your data is present. So there only what happens? These task tracker is going to work, monitor, and gives the result back to the job tracker. It is reduced. See, that's why it is two-way, signal. So one way it is coming, the map process the entire thing, and reduce results will be sent back to the job tracker. Inside the job tracker, you have final reducer that will reduce the jobs, that will reduce the results, that will reduce the output of the job. So entire output of the job, whatever it is being submitted, the entire job's output is being collected at the job tracker itself. And observe here, this is again, it is a name node, and these are all running in data nodes. The job tracker coordinates all the jobs running on the system by scheduling the tasks and to run the task tracker. And very, very, very important thing. So you are talking about only one client, one job. There are occasions, there are situations where a client will submit 2-3 jobs simultaneously, multiple jobs simultaneously. Multiple jobs are again handled by a single job tracker. Okay, single job tracker, and it will be coordinated among many task tracker. For a job one, some tasks are there. For job two, there are some tasks are there, task trackers. So everything is coordinating by your job tracker, and you should understand very well. It's just like client server. Whatever you are writing your, your PHP program or JSP program, whatever you are writing. So for every request, it will have the response, and there server alone will manage. Here, the job tracker will manage. One client's request, it will manage using the task trackers. There are many task trackers for each job, right? And of course, task trackers runs the track and sends the progress report to the job tracker. And very, very important. There was again somebody is asking in the chat box, sir, how failed? Suppose there is a issue with the job tracker. Okay, some issue with the job, some task tracker. One issue it has happened here. So how it will come to know? Job tracker will come to know. Somebody is asking in the group, in the chat. Good. Okay. See, every time, whenever task is being performed, every time the task is being performed, the task tracker will send the progress report. Send the progress report to the job tracker. Just like you have data nodes sending heartbeat signals, the block reports, heartbeat signal to the name node, same way the task progress report is sent by each task tracker to the job tracker. Every 2 seconds, every 3 seconds it will be sending, or every 5 seconds, take for example, 5 seconds. That can be configured again. It can be configurable. As an administrator, you can easily configure, right? Once the configuration is done, of course, every 5 seconds. Every 5 seconds, what happens? The task trackers will send the overall progress reports. And these progress reports will tell that the progress is happening. The task is happening. There is no problem with the task tracker. Suppose progress report is not received. Suppose any progress report is not received from particular task tracker or from a particular name node. So in such situation, the job tracker will understand, oh, there is a problem with this particular node. So particularly, so if remember this particular task tracker has not sent the progress report. Okay, so whatever that task that has been allocated, to this particular task will be parallelly allocated to another machine. So where you have both mapper and reducer. Map and reducer. Your task tracker will allocate to another. Parallelly, it will allocate. So, and get the job done. So this is how it will track the jobs. Okay. So task tracker runs the tasks and sends the progress report to the job tracker, which keeps the record of the overall progress of each job. If a task fails, the job tracker can reschedule it on a different task tracker. Task tracker is nothing but it's a different machine. It's a different machine. I can certainly say it's a different machine. So where the entire operation is done. Entire operation is done. So that's the one you should understand. And Further, the mapper does a lot of very useful thing. Mapper does a lot of useful thing, and mapper is actually runs on map function. Runs on map function. So what happens when an input is given? Here, whenever an input is given, so your input is split into many parts, and later it is sent as a record reader to the map, and map is actually a function. Map will going to execute this data, execute the operation on this data, and finally it will send the result to intermediate. That is, it has to go to the next stage. So before it goes to the next stage, what happens? It will be put in the intermediate stage, in between stage. So Hadoop divides the input. Hadoop divides the input to MapReduce. It will reduce the input to MapReduce job into a fixed size called input splits. Input splits. Entire job is split into input splits or just splits. Hadoop creates a map task for each of this split. So for every split. So in our case, in our example, so it's 100 years data we are having. So when we have 100 years of data, every 10-year data is allocated to one map. So that input split is taken care by your mapper. So mapper is the entire operation management. We call it as a mapper. Okay, having many splits means the time taken to process each split is small compared to the whole process. Of course, definitely, when you split the job into small tasks, what happens? Each task is being executed. Each task is being executed parallelly, simultaneously. Is executed parallelly, simultaneously. So what happens when it is executing simultaneously? Certainly, time will be reduced. That's what. If you do the whole process completely simultaneously by a single processor, and single process or single job, so what happens? Time will be more. If the same split into many pieces, and if it is done by each job is divided into tasks, and if it is parallelly executed, so definitely it will reduce. So if you are processing the split in parallel, the processing is better. The load is balanced if the splits are small, since the faster machines will able to process proportionately more splits over course of a job than slower machines. Certainly, it is the same thing. On the other hand, if the splits are too small, then the overhead of managing the splits and MapTop's task creation begins to dominate the total job execution. So, if the data size is very less than 64 MB, so what happens if you apply this MapReduce to small data? Definitely, the entire management, splitting, joining, the coordination, checking whether task is happening or not, all those things will take a lot of resources. So it will be a costly affair. It will not be suggested. When the data is big, So definitely, this MapReduce operation you can certainly implement, and it will work. So on the other hand, if the splits are too small, then the overhead of managing the splits if the splits are small, the split is small, input split, or the whatever the split is small. So if it is too small, for every 6 months, if you split, data is very small. It is not worth. So instead of splitting for every 6 months, you split for every 10 years. So it becomes somewhat big. Also, it can be processed simultaneously. So the idle, split size normally will be 64 MB is the idle. So if you have a data of 64 MB you split, or data of 128 MB you split, that will be very idle. That is the reason the block size is also maintained 128 MB or 64 MB. Block size. In the HDFS, we have understood right. I told. Every block will have either the size of 64 MB or 128 MB. This is the reason. If you have lesser block size, what happens? Each block will be allocated to one task tracker, and of course, the entire management itself, it is very difficult. So in order to overcome all those things, they have experimented this on various sizes, and finally the scientists, computer scientists, have come to a conclusion that 64 MB is idle or 128 MB is idle. Because if your processor is somewhat, today we are getting i7 process, higher end processors. So comparingly, all those things, if you compare, so definitely 64 MB is idle. So this is what we have for today's class. That's all for today's class. My humble request to you, kindly attend all the sessions. Another maybe 1 week or so, 1 week or 10 days, we may run the entire online classes. We'll complete the syllabus. We'll do tests. Kindly respond to all the tests. I know many are facing difficulties, but that should not stop your learning. That should not stop your progress. Okay. With all these things, I end today's class. Today's class recording is again it's available online in this particular website, and also study material is also available in this website. That's all for today's class. Thank you. Have a wonderful day.